Namaskar, my dear friends. Let us talk about a GaNFET high efficiency DC-DC converter that we have designed. So what we will do is we have taken an input voltage here and we will be getting an output voltage here. Okay. And the output, as you can see, it is quite high. It is going to be 15 volt, 15 ampere rating. The IC that I am going to discuss is LTC7891, and there is a very nice features for this IC is it can set you without giving you any feedback resistor divider, 12 volt and 5 volt setting. Okay, so this also I'll give it to you. However, let us first discuss about this particular IC detail, and then we will go ahead with our design and detail. And before that, the design requirement that we will be discussing is we have some design requirement that is there from a specific application, that for that we have developed this particular circuit. So the input voltage range from 18 volt to 36 volt. The nominal voltage input is 24 volt from a battery. Okay. The output voltage that is there is 15 volt and 15 amperes rating. Let us say we have been decided that ripple voltage is 1 volt RMS, and the voltage tolerance we have decided 5%. You can achieve it, like approximately 1% as well. Okay, so there is no need to go ahead 1%. That's the reason we have kept it 5%. So in the voltage terms, it is going to be 0.75 volt. There is a overload trip volt current. So overload trip current, what will happen is at 130% of current rating, it will trip automatically. Okay, which is going to come up 19.5 ampere. If you wish to, you can increase it to, let us say, 135% or 140%, something like that, not a problem. The efficiency we are maintaining minimum, it is 95%, but it is reaching up to 98% as well from the design point of view. And the temperature range is working as 0 to 70 degrees centigrade. Okay. Generally, if you see in this kind of like devices, your temperature range will be generally 0 to 40 degrees centigrade environment, and so that it can the IC can reach up to around 100 degrees centigrade. It won't be a problem. And there are design equations that we'll discuss once we discuss the IC detail. All right. So let us start this GaNFET driver IC one by one. So as you can see, you come to the web page of this particular analogdevices.com. We see LTC7891. This is a very nice IC of 100 volt capability, synchronous step down controller for GaNFETs. Okay. And there are a few, circuits that is already given. And this list price is also $2.09, which doesn't matter actually because pricing will not matter for this kind of applications. However, this is a very low price IC. There are a lot of features and additional benefits and all these things are there. However, I will talk about only application right now. So application, you can see we have industrial power systems, we have military avionics and medical systems. Medical systems, the application that we have utilized is for like CT scan and MRI. For that rating only we have used this particular DC-DC converter. And we have a capability to be used in telecommunication power systems as well. So this is how it is going to be beneficial for all military application, like medical devices and industrial power systems, as well as telecommunication power systems. So this is what we have from the analog devices website. And the best part is they have three, reference designs. You can see we have evaluation board LTC7891-BZ. Then we have AZ. So AZ is the one which we have taken as a reference for our design because it is having, like GaNFET with little bit higher voltage rating. And one more is, DC2995. So this is also can be used as a reference design. However, we have referred this one. Okay. So let us start with the data sheet of this particular device. So you can see we have LTC7891. As you can see, some of the features that if you talk about, it can drive GaNFET technology fully optimized for GaNFETs. Okay, so that's the requirement these days. And the input voltage range is 4 volt to 100 volt. So this is primarily suiting for our application, which is 18 volt to 36 volt input voltage. The output voltage can be set from 0.8 volt to 60 volts. So we are actually setting my output volt to 15 volt. We have no requirement of like a catch diode or clamp diode or bootstrap diode. All these things are no required externally. We have internal smart like bootstrap switches prevention, overcharging for high driver switches, and all those other functionalities are there, as like we see in the normal DC-DC converters. Like we have programmable frequencies and like accurate adjustable driver output under lock voltage and over voltage drop, over voltage protection. All these things are there. We have 28 lead like package, which is in form of QFN package. And as I already mentioned you about the applications, so it can be used for your industrial power systems, military avionics, and medical devices. So this is the reason like you can utilize this in as well as in automotive application also. Okay. So this was all about the general specification for this device. Now let me walk you through a complete design procedure for this particular device. So we will start with one by one. Right now you can see the revision is 2022, so it is very new IC, which is very much recommended for your new design. Coming back to electrical parameters, we already seen the temperature, voltage input range is 4 to 100 volts. So 18 to 36 volt is very much applicable for our design. So what I'll do is from electrical parameter, we'll take only those points which is necessary. Okay. So first of all, we need VPRG pin floating, which is zero 0.8 volt. If it is floating, then it will give you 0 0.8 volt. Or if you want, you can set the output voltage by using VPRG pin. So this is very, very important pin from the IC. So if it is 0 volt, the output will be 5 volt. And if it is int VCC, so then it will become 12 volt. So this is how you will be setting a fixed voltage output for 5 volt as well as 12 volt. So this 12 volt setting and 5 volt setting is very, very easy. However, if you do not want to set fixed 5 volt and 12 volt, then you leave this particular pin floating, and in this way you will be able to put a like a feedback resistor divider setting, and in that way you can program it for 0.8 volt. This is how you will be able to set your some other regulated voltage output. Okay. So this was all about this. Coming back to VSense pin is very, very important. So here you are going to set your, like if it is I limit is floating, then it will be, like 50 millivolt. If it is 0 volt, then it can be set 26 millivolt. And if it is int VCC, then it will be 75 millivolt. Okay. So how much current limit you want to set, it depends on that. So if you want to set a higher current limit, you have to put I limit to int VCC. If you have to put lower limit, you have to ground it. Okay. So once you ground it, it will be limited to lower current rating. However, what we have done is we have put it floating so that we have a medium range of current limitation. Coming back to iSense current pins, so we have positive and negative current sense pins across which like a current sense resistance will be connected, and this is how we will be measuring the current passing through the current sense resistor. Okay, so this is how it will be working. So hope you have like followed completely all these points till now. Let us now proceed to next point. So next point is we have like a gate driver. So gate driver, we have top side pull up and pull down pins. So pull up and pull down pins are there, which is going to like set based on what is there. However, they have what is the typical range of like ohms. So basically it is like a 2 ohm and 1 ohm or something like that. You can put it down for top side and bottom side. We have bootstrap and DRVCC set on resistances. All these things are not required right now for my point of view. We'll see all these points during the like design equations. Coming back to LDO. Okay, so there is int VCC which is going to give you an LDO output, and this is very important. Either it can be driven through like a V-in pin or external voltage that can be like a tied up from the output voltage that you have made, right? So V out, let us say we have 15 volt. So this 15 volt can be given as a supply to this int VCC LDO. This is how you will be actually increasing the efficiency. So if you want to increase efficiency, you can supply int VCC regulator by an external voltage, which is going to be, let's say, output voltage itself. because input voltage V in actually varies quite high, and that's the reason efficiency may go little down. Now we will set DRV set to 0, let us say, then it will be 5 volt. If you want to set little bit lower or some other values, you can set it as well, or you want to set it to 5.5 volt, you can do that as well. Okay, but we will set it by default 5 volt. Next is we have some frequency spectrum. So as you can see, we have fixed frequency and we have low frequency, high frequency, programmable frequency features. So what we have done is we can program it from 370 kilohertz to around 2.25 megahertz. However, what we have done is we have made it to 500 kilohertz. So 500 kilohertz is a optimal frequency of operation for this kind of applications, and for that purpose you can put 75 kilo ohm for that. Otherwise exact calculation comes as 73 point 2 kilo ohm, so that also you can put. Similar to that, we have power good pin. So power good pin actually tells you like what is the situation. So once there is a problem, the power good pin goes low, otherwise it will be high. Okay, so when it is high, you will be seeing that my output voltage is good condition, like it is plus minus 10% or within the range. When it is high, then you have to make sure that this is actually open drain pin. In that case, you have to put a pull up resistor, then only it will be high, otherwise it won't be going high at all. Okay, so if you wish to, you do not want to see the power good output or something like that, you can leave it open, otherwise you pull it high and keep it as it is. So this was all about the electrical parameters. Coming back to next part, absolute maximum rating, there is no requirement right now. We can skip that. We have already seen these all in detail in our regular sessions very properly, right? So hope you have a good understanding about DC-DC converters, how they are designed. Now coming back to pin configuration. So this is very nicely packaged in 28 pin package, and as you can see, we have pin number 1 to 8 like this, and 9 to 14, and 15 to 22, and this is how we have 23 to 28. We have ground pin, which is actually in terms of exposed pad, that is there at the bottom of the IC. So this exposed pad is nothing but your ground, that will be utilized as a ground pin. In addition to that, what we have is we have proper functionality of each and every pins and their description. So we will skip right now because we already know like how to design this, so that I will tell you during the design phase itself. Okay, let us proceed to quickly design phase. So what I will do is I'll come down and go into the applications. So this is well recommended. I see why, because I have utilized by myself personally for this particular applications, and as well as for high current application and very high efficiency requirement. This is one of the best IC that I have gone through. Okay. So let us talk about theory of operation. So theory of operation is basically it is a normal DC-DC converter which is actually driving your MOSFET. So it is not going to drive a MOSFET. Now we will be utilizing GaNFET, and basically GaNFET that we are taking, actually we have utilized in our application from EPC. So EPC is one of the best company for GaNFET devices. So if you want, you can choose the GaNFET from them as well, or otherwise you can always choose it from Infineon as well. So Infineon is also one of the best company for GaNFETs. Coming back to the next parts, so let's come down. Application information. Okay, so very first thing is we have inductor calculation, and similar to that other parts are there. So before that, what we'll do is, you can see the basic LTC 7891 application circuit. Actually it starts from external component selections. So what happens is you have to start with selection of your inductor, your current sense components, your operating frequency range, your light load component, operating modes. Then we have remaining power stage components like FETs and all those things, like input capacitor, output capacitors, FETs. All these things can be chosen, right? Then let us say you want to set the voltage level. So for that you have to put feedback resistors so that you can set a desired output voltage, and then remaining external components as and when we can select. Like that, like you have to have soft start timing, biasing, and loop compensation circuitry. All those things can be also done. Okay, so this is how you can do that. So as I told you, like I have also like I mean seen the evaluation board, so that also you can take into account. Okay. So let us start with like slowly going forward in this. We will start directly our design equation. Before that, I'll just give you a brief idea about the evaluation board. Okay. So once we go to the evaluation board, you can see this is the evaluation board, very nicely made. Okay. So you can see we have the like a stub here, that is the input connector. This is the output connector. So this is how, since it is very high current, so you have to have like a through hole connectors kind of thing. Okay. Some other pictures, if you can see, this is the top view and this is the bottom view that is there. All right. If you see the circuit, so very nicely they have made like like they have made a lot of capacitors in parallel, and like 47 microfarad, 47 microfarad, 22 microfarad and all these things. However, our application is little different, so our changes will be little different based on the design equations. Okay. However, you also have to maintain your like very nicely how input connectors and all can be connected, how you can give test points and external test points and all, how you can give some extra capacitors for the later purposes, how you can run separately run pin, or if you want to permanently run it on like that also you can do. So all these things you can do it slowly. So instead of going through this circuit, what we'll do is we'll go ahead with our design. Okay. This is your output capacitor and this is the current sense resistor. We have the like inductor, and this then we have the like EPC 2218. So 2218 is the device that they have utilized. We have used some other because our application is little different, and this is how like a switching pin is driving the like drain of this particular MOSFET and source, right? So drain and source, in the middle it is connected. Similar to that, we have like a top gate driver and bottom gate driver. So both are there, and we have current sense pin here that is connected here. Okay. So this one you can anyway go ahead with by yourself. Okay. So what we can do now is, if you want to go ahead with complete design of their evaluation board, this is the particular like 11 page evaluation board user guide is there. So nicely you can read out, and first you can like test with this particular evaluation board, and then only you can go ahead with your design. However, what we have designed, we will start explaining one by one. Okay. So this is the board that is there like given by them. So they have given this particular circuit, and what we will do is we will proceed with our design. Okay. So this is the bill of material that they have given. However, our like things are also almost better than this. Okay. So let us start with our design. So as you can see, like this is our design that is there for 15 volt, 15 ampere. And what we'll do is let us continue this session in our next video. Thank you.